The formation of atoms from nothing is one of the most profound questions in physics, cosmology, and philosophy. To understand how this process occurred, we must first define what we mean by nothing. In common language, nothing implies absolute emptiness, a complete void devoid of any substance. However, in physics, nothing is a much more complex concept. Quantum mechanics and relativity suggest that even what appears to be a vacuum is not truly empty, but filled with fluctuating energy and virtual particles. This is the foundation upon which modern physics builds its explanation of how matter, and ultimately atoms, came into existence. The story begins approximately 13.8 billion years ago with the Big Bang, the event that created the universe. The prevailing scientific consensus is that the universe originated from an incredibly hot and dense singularity, where all the mass and energy of the cosmos were concentrated into an infinitesimally small point. At the moment of the Big Bang, this singularity began to expand, marking the birth of space and time. But what existed before the Big Bang? This remains one of the biggest mysteries in cosmology. Some theories suggest that the universe emerged from quantum fluctuations within a pre-existing vacuum, while others propose that it was a result of cyclical cosmic expansion and contraction. Regardless of its origin, the immediate aftermath of the Big Bang was characterized by unimaginable temperatures and energy densities. During the first Planck time, 10 Menenziucom-seconds after the Big Bang, the known laws of physics break down, making it difficult to fully comprehend the state of the universe. However, as the universe expanded, it cooled rapidly, allowing fundamental forces to differentiate from a unified state. These forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, governed how energy transformed into matter. According to Einstein's famous equation, E=mc², energy and mass are interchangeable. This principle is crucial for understanding how particles emerged from the energy of the early universe. The first fundamental particles to form were quarks and leptons, which are the building blocks of all known matter. At extremely high energies, pairs of particles and their corresponding antiparticles spontaneously emerged from the quantum vacuum, only to annihilate each other almost instantaneously. However, due to a still unexplained asymmetry known as baryon asymmetry, a slight excess of matter over antimatter existed, allowing some particles to survive the annihilation process. As the universe continued to expand and cool, quarks combined to form protons and neutrons in a process governed by the strong nuclear force. This period, known as baryogenesis, occurred within the first millionths of a second after the Big Bang. However, the early universe was still too hot for atomic nuclei to form, as high-energy photons continuously broke apart any newly formed structures. It wasn't until approximately 3 minutes after the Big Bang that the temperature had dropped sufficiently to allow protons and neutrons to fuse, giving rise to the first atomic nuclei. This process, known as Big Bang nucleosynthesis, led to the formation of the lightest elements, primarily hydrogen and helium, with trace amounts of lithium and beryllium. These elements would later serve as the building blocks for the formation of stars and galaxies. However, even at this stage, atoms as we know them did not yet exist, as free electrons were still roaming the universe, preventing the formation of stable atomic structures. For the next 380,000 years, the universe remained in a hot, dense plasma state, where photons continuously scattered off free electrons, making the cosmos opaque. This period ended with an event known as recombination. As the universe cooled to around 3000 K, electrons combined with atomic nuclei to form neutral atoms, allowing light to travel freely for the first time. The photons released during this era can still be detected today as the cosmic microwave background radiation, CMB, providing us with a glimpse into the infant universe. With atoms now formed, the next major phase in cosmic evolution was the formation of large-scale structures. Initially, the universe was nearly uniform, with tiny fluctuations in density. However, under the influence of gravity, these fluctuations grew over time, leading to the formation of massive clouds of gas that eventually collapsed to form the first stars and galaxies. Inside the cores of these first-generation stars, nuclear fusion began, transforming hydrogen and helium into heavier elements such as carbon, oxygen, and iron. This process, known as stellar nucleosynthesis, played a crucial role in enriching the universe with the elements necessary for the formation of planets and life itself. When these massive stars reached the end of their life cycles, they exploded in violent supernovae, scattering heavy elements into the surrounding cosmos. These elements then became incorporated into new generations of stars and planetary systems. Over billions of years, this cycle of star birth, fusion, and destruction created the chemical complexity required for life to emerge. The question of whether atoms truly emerged from nothing depends on how we define nothing. If we take a strict philosophical perspective, meaning absolute emptiness with no laws, no space, and no time, then the origin of matter remains a profound mystery. However, if we accept the definition of nothing as a quantum vacuum where virtual particles can spontaneously appear and disappear due to quantum fluctuations, then the formation of atoms can be explained through well-established physical principles. Modern physics suggests that even empty space is not truly empty. The Heisenberg uncertainty principle allows for the brief existence of virtual particles, which can momentarily pop in and out of existence. In certain conditions, such as those present during cosmic inflation, these fluctuations can be amplified, leading to the creation of real particles and, eventually, matter. Experiments at the Large Hadron Collider, LHC, and observations of the Casimir effect provide evidence for these quantum phenomena, supporting the idea that nothing, in a physical sense, is an active and dynamic state. Additionally, the discovery of the Higgs boson in 2012 provided a crucial piece of the puzzle regarding how particles acquire mass. The Higgs field permeates space, and as particles interact with it, they gain mass, allowing them to form stable structures, like atoms. Without the Higgs mechanism, all particles would remain massless and incapable of forming the complex structures necessary for the existence of matter as we know it. Despite these advancements, many unanswered questions remain. What caused the initial conditions of the universe? Why did matter prevail over antimatter? Could there be other universes with different physical laws? Some theories, such as the multiverse hypothesis, suggest that our universe is just one of many, each with its own unique properties. If this is the case, then the emergence of atoms may not be a singular event, but rather a natural consequence of underlying physical principles governing all of reality. The implications of understanding how atoms formed from nothing extend beyond physics and cosmology. They touch on fundamental philosophical and existential questions about the nature of existence itself. If matter can emerge from the quantum vacuum, does this challenge traditional notions of creation? What does this mean for our understanding of time, space, and reality? Such questions push the boundaries of human knowledge and inspire further scientific inquiry. Future research in fields such as quantum gravity, string theory, and observational cosmology may bring us closer to answering these profound questions. With advancements in technology, including next-generation telescopes like the James Webb Space Telescope and particle accelerators capable of probing the fundamental nature of reality, we are on the verge of uncovering deeper insights into the origins of matter and the universe itself. Ultimately, the formation of atoms from nothing is a testament to the power of physics to explain the seemingly inexplicable. From the chaotic aftermath of the Big Bang to the formation of galaxies, stars, and life itself, the universe follows a set of natural laws that allow complexity to emerge from simplicity. The journey from nothing to something, from energy to atoms, from atoms to stars, and from stars to conscious beings capable of pondering their own origins, one of the greatest scientific narratives ever told. As we continue to explore the cosmos and push the boundaries of our understanding, we may one day uncover the ultimate answer to why there is something rather than nothing. Until then, the story of how atoms formed from nothing remains one of the most fascinating and awe-inspiring tales in the history of science. The evolution of humanity's understanding of the universe, a historical perspective. Since the dawn of civilization, humanity has gazed at the night sky, searching for meaning in the vast expanse of the cosmos. From ancient mythologies to modern astrophysics, our understanding of the universe has evolved through a combination of observation, mathematical reasoning, and technological advancements. This journey has been marked by revolutionary discoveries that challenged established beliefs, ultimately leading to our current understanding of the observable universe. 1. The ancient conception of the cosmos. The earliest recorded attempts to understand the universe date back to ancient civilizations such as the Babylonians, Egyptians, Chinese, Greeks, and Indians. These early cultures relied on mythology, religion, and rudimentary astronomical observations to explain celestial phenomena. In Mesopotamia, the Babylonians, circa 2000 BCE, developed one of the earliest known astronomical systems, creating detailed star catalogues and predicting planetary movements. Their understanding was largely geocentric, Earth-centered, and celestial events were often interpreted as omens. The ancient Egyptians also studied the stars, primarily for agricultural and religious purposes. They aligned their pyramids with specific constellations and developed a calendar based on the heliacal rising of Sirius, which helped predict the annual flooding of the Nile. In China, astronomers carefully tracked celestial events, such as eclipses and supernovae, and kept extensive records that would later prove valuable to modern science. 2. The Greek contribution, the birth of rational astronomy. The ancient Greeks laid the foundation for scientific cosmology by introducing logical reasoning and mathematical analysis into astronomy. Thales of Miletus, circa 600 BCE, proposed that celestial bodies followed natural laws rather than divine will. Pythagoras, circa 500 BCE, suggested that the Earth and other celestial bodies were spherical. Plato, circa 400 BCE, and Aristotle, circa 350 BCE, advanced the geocentric model, arguing that the heavens were composed of perfect, immutable spheres revolving around the Earth. One of the most significant contributions came from Claudius Ptolemy, circa 150 CE, whose Almagest refined the geocentric model using complex epicycles to explain planetary motion. His model remained dominant for over a millennium. 3. The scientific revolution, heliocentrism, and the fall of geocentrism. During the Renaissance, a dramatic shift occurred as new observations and mathematical models challenged the long-held geocentric view. Nicolaus Copernicus, 1543, proposed a heliocentric, Sunday-centered model, arguing that the planets orbited the Sunday rather than the Earth. His book, De Revolutionibus Orbium Coelestium, laid the groundwork for modern astronomy. Johannes Kepler, early 1600s, refined Copernicus's model by discovering that planets move in elliptical, not circular, orbits described by his 3 laws of planetary motion. Galileo Galilei, 1610, used a telescope to provide direct observational evidence against the geocentric model. He discovered moons orbiting Jupiter, phases of Venus, and surface imperfections on the Moon, contradicting Aristotle's idea of perfect celestial spheres. This period marked the transition from an Earth-centered cosmos to a dynamic, heliocentric system governed by natural laws. 4. Newtonian mechanics and the universe as a machine. In the late 17th century, Isaac Newton, 1687, revolutionized our understanding of the universe with his work Principia Mathematica. Newton formulated the laws of motion and universal gravitation, demonstrating that the same force governing falling objects on Earth also governs planetary orbits. His work provided a mathematical framework that unified celestial and terrestrial physics, reinforcing the heliocentric model. 5. The discovery of the expanding universe. For centuries, astronomers assumed that the universe was static and unchanging. However, this idea was challenged in the 20th century. Albert Einstein, 1915, developed the general theory of relativity, which described gravity as the curvature of spacetime. Initially, Einstein added a cosmological constant to keep the universe static, but later admitted this was a mistake. Edwin Hubble, 1929, discovered that galaxies are moving away from us, with their light redshifted due to the Doppler effect. This provided the first observational evidence that the universe is expanding, leading to the Big Bang Theory. 6. The Big Bang Theory and the birth of modern cosmology. The idea that the universe began as a singularity and expanded over time was first proposed by Georges Lemaitre, 1927. In the following decades, physicists developed this into the Big Bang Theory, which is now the leading explanation for the origin of the universe. Arno Penzias and Robert Wilson, 1965, discovered the cosmic microwave background radiation, CMB, the afterglow of the Big Bang, providing strong evidence for the theory. Alan Guth, 1981, proposed the inflation theory, suggesting that the universe underwent an exponential expansion in the first fraction of a second, explaining why it appears homogeneous and isotropic on large scales. 7. The space age and milestones in exploration. With advancements in technology, humanity transitioned from merely observing the universe to exploring it firsthand. 1957. The Soviet Union launched Sputnik 1, the first artificial satellite, marking the beginning of the space age. 1961. Yuri Gagarin became the first human to travel to space. 1969. The Apollo 11 mission successfully landed astronauts on the Moon, with Neil Armstrong becoming the first person to walk on its surface. 1977. NASA launched Voyager 1 and 2, which continue to send back data from interstellar space. 1990. The Hubble Space Telescope was deployed, providing some of the most detailed images of distant galaxies and helping refine estimates of the universe's age. 2004 to 2021. The Mars rovers explored the Red Planet, uncovering evidence of past water activity. 2021. The launch of the James Webb Space Telescope, JWST, promised a new era of deep space observation. 8. The concept of the observable universe. While the universe is vast, we can only see a finite portion of it, the observable universe. This is the region of space from which light has had time to reach us since the beginning of the Big Bang, limited by the speed of light and the universe's expansion. The observable universe is approximately 93 billion light-years in diameter. Due to cosmic expansion, many galaxies we see today are actually much farther away than their observed distance due to the stretching of space. Beyond the observable universe, there may be regions of space that we will never be able to access. The existence of an event horizon suggests that some parts of the universe are permanently beyond our reach. This raises profound questions about the nature of reality and whether other universes exist beyond our observational limits. Conclusion: the unfinished quest for understanding. Our journey in understanding the universe has been shaped by centuries of observation, scientific revolutions, and technological breakthroughs. From ancient myths to the laws of physics, humanity's perception of the cosmos has continuously evolved. Each discovery has opened new doors while raising deeper questions. As we continue exploring space, developing new telescopes, and advancing quantum physics, we move closer to answering fundamental questions. What is the fate of the universe? Is there life beyond Earth? What lies beyond the observable cosmos? The quest for knowledge is far from over, but with each step forward, we unravel the profound mysteries of the universe-own discovery at a time. The universe is vast beyond comprehension, a seemingly infinite expanse of darkness and light, filled with galaxies, stars, and mysteries that stretch far beyond the limits of human imagination. But why should people care about it? Why does it matter to us, tiny beings on a small rock orbiting an average star in a quiet corner of an ordinary galaxy? The answer lies deep within us, woven into the very fabric of our consciousness, in the unshakable curiosity that has driven us since the dawn of humanity. The cosmos is not just an empty void, it is a mirror reflecting our deepest fears, our greatest hopes, and our most profound questions about existence itself. From the moment we became aware of the sky above, we have sought meaning in its endless abyss, staring up at the stars and wondering what lies beyond, where we came from, and if we are alone. There is something inherently humbling about the realization that we are part of something so incomprehensibly vast, something that existed billions of years before us and will continue long after we are gone. This perspective forces us to confront the fragility of our own lives, the fleeting nature of human existence, against the backdrop of a cosmos that operates on a scale so immense that entire civilizations rise and fall in the blink of a cosmic eye. It is a source of both awe and terror, a realization that can be both freeing and deeply unsettling. The boundless nature of the universe reminds us of our insignificance, yet paradoxically, it also fills us with an undeniable sense of wonder. There is beauty in knowing that the atoms that make up our bodies were forged in the hearts of dying stars, that the elements essential for life itself were created through cosmic violence, supernovae scattering heavy elements across the galaxies, seeding the conditions for planets, for oceans, for life to emerge. It is a realization that binds us to the cosmos, making us not separate from it, but a direct product of its infinite processes. When we look up at the night sky, we are not just seeing stars, we are looking at our own history, at the origins of everything we know. The further we gaze into the depths of space, the deeper we look into our own past, tracing the journey from the formation of the first atoms to the emergence of galaxies, to the creation of the Sunday, the Earth, and ultimately, us. But with this knowledge comes an inevitable existential unease, a confrontation with the unfathomable distances, the cold, empty void between stars, the inescapable silence that defines the universe beyond our small world. The sheer scale of it all forces us to question our place within it, whether we are truly alone in this vast, indifferent expanse, or whether somewhere, among the countless stars, other conscious beings stare up at their own night sky, wondering the same thing. This duality, this balance, between wonder and fear is what makes the universe so deeply compelling. It is what has driven humanity to explore, to reach beyond the confines of our planet, to build telescopes capable of peering billions of light years into the past, to send probes into the void, hoping to find answers. It is why we have searched for signals from distant civilizations, why we dream of stepping onto new worlds, why we have risked everything to touch the edge of the unknown, because in that vast emptiness, we see the ultimate challenge, the ultimate mystery, one that is far greater than ourselves, yet inseparably linked to our own existence. It is not just about scientific curiosity, it is about something deeper, something primal, the relentless need to understand, to seek, to push beyond the boundaries of what we know. The universe is, in many ways, a reflection of our own nature, expansive, unpredictable, filled with both chaos and order, destruction and creation, questions and discoveries. It embodies the very essence of what it means to be human, to be small, yet capable of immense thought, to be insignificant, yet filled with limitless imagination. The cosmic void does not just inspire scientists and astronomers, it inspires artists, poets, philosophers, and dreamers alike. It forces us to think beyond the confines of our everyday lives, beyond the struggles and routines, beyond the immediate concerns of our own existence, and into the realm of the infinite. It humbles us, reminds us of our place in the grand scheme of things, and yet, at the same time, it elevates us. Because despite our smallness, we have the unique ability to perceive, to wonder, to ask the questions that define our very being. And perhaps that is the greatest reason why people should care about the universe, not just because it holds the answers to where we came from and where we are going, but because in understanding it, we come closer to understanding ourselves. Have you ever looked up at the night sky and felt a sense of wonder, a deep, inexplicable feeling that you are staring into infinity, into something far greater than yourself? Have you ever questioned why anything exists at all, why there is something rather than nothing, why the universe, in all its vast complexity, came into being? These are not just abstract philosophical musings, they are fundamental questions that lie at the very heart of our understanding of reality, shaping the way we perceive existence, time, and our own place within the cosmic order. Every discovery we make about the universe challenges the way we see ourselves, forcing us to rethink our origins, our future, and even the very fabric of reality itself. If we could answer the deepest mysteries of the cosmos, would it change the way we live, the way we love, the way we dream? Or would it only open doors to even greater, more perplexing questions that stretch beyond the limits of human comprehension? Imagine for a moment that we discover undeniable proof of life beyond Earth, not just microbial organisms beneath the icy crust of Europa or within the clouds of Venus, but intelligent civilizations, beings who have looked up at their own skies and wondered the same things we do. How would that change everything we know about ourselves? Would it unite humanity in the realization that we are not alone, that we are part of a much grander cosmic community? Or would it fracture our sense of uniqueness, disrupt religions, cultures, philosophies, and challenge everything we thought we knew about our significance in the grand scheme of the universe? Even if we are alone, at least in this moment, what does that say about us? that in all the endless galaxies, in the trillions upon trillions of stars, in the infinite cosmic void, we are the only ones who can think, who can ask, who can wonder. If that is true, does it not make existence even more precious, even more meaningful, that out of all the chaos and energy and physics of the universe, consciousness has emerged here on this small, pale blue dot? But these questions go beyond just the search for life. What if one day we discover the true nature of dark matter, the invisible force that holds galaxies together, the unseen substance that makes up most of the universe's mass? What if we unlock the secrets of dark energy, the mysterious force accelerating the expansion of the universe, stretching space itself, driving galaxies apart at speeds beyond comprehension? Would such a discovery bring us closer to understanding the fate of the universe? Would it mean that one day, billions of years from now, everything will drift into an infinite darkness, where even atoms themselves decay, leaving behind a silent, empty void? Or could it mean something else, something even stranger, an ultimate cycle of rebirth, where the universe collapses in on itself only to be reborn in an endless sequence of big bangs, an eternal recurrence of existence itself? Then there is the greatest question of all, the question of reality itself. Are we truly perceiving the universe as it is? Or are we limited by the constraints of our own biology, our own senses, our own minds? Could it be that reality is something far stranger than we have ever imagined? That the universe is not merely a vast collection of stars and galaxies, but something far more complex, perhaps even something simulated, something designed, something constructed on a foundation that we are not yet capable of comprehending? Some physicists suggest that the fabric of reality is deeply tied to information, that space, time, and matter may not be fundamental at all, but emergent properties of something deeper, something akin to a cosmic algorithm, an underlying code that generates everything we see and experience. If that were true, what would it mean for free will, for consciousness, for the very nature of existence itself? These are not questions meant to be answered in a single moment, nor are they simply intellectual exercises. They are the driving force behind humanity's relentless pursuit of knowledge, the fire that has pushed us to build great observatories, to launch telescopes into the depths of space, to send probes beyond our solar system, to dream of traveling among the stars. Every great scientific breakthrough has begun with a question, a willingness to challenge what is known, to look deeper, to explore further. And now, we are on the precipice of the greatest discoveries yet to come. The James Webb Space Telescope is peering into the earliest moments of the universe, unraveling the story of cosmic dawn, searching for the first galaxies that formed in the wake of the Big Bang. The next generation of space missions may bring us face to face with habitable exoplanets, worlds with oceans, atmospheres, perhaps even civilizations waiting to be found. Theoretical physicists are working tirelessly to bridge the gap between quantum mechanics and general relativity, seeking a unified theory that could reveal the fundamental structure of reality itself. But what role do we, as individuals, play in this grand cosmic journey? It is easy to feel insignificant in the face of such vastness, to see ourselves as tiny, fleeting specks in an indifferent universe. Yet, paradoxically, the very act of asking these questions, of contemplating the infinite, is what makes us significant. We are not just passive observers of the cosmos, we are participants in its unfolding story. Our curiosity, our imagination, our drive to understand is what sets us apart, what elevates us beyond mere existence. Each of us has the ability to contribute to this search for meaning, whether through science, through art, through philosophy, through discussion, through the simple act of wondering. Every new perspective, every new insight, every new dream adds to the collective pursuit of truth. And so, the question is not just about what the universe is, but about what it means to us. How does it shape our perspective on life, on death, on purpose? Does knowing that we are made of stardust, that the atoms in our bodies were forged in the fiery deaths of ancient stars, change the way we see ourselves? Does understanding that our time here is temporary make life more precious, more urgent, more meaningful? When we think about the possibility of a multiverse, of parallel realities, of dimensions beyond our perception, do we feel excitement, fear, or a mix of both? Does the knowledge that one day the Sunday will consume the Earth that our species may one day face extinction make us cherish the present moment more deeply? Or does it push us to dream bigger, to ensure that humanity extends beyond this one fragile world, to become a spacefaring civilization, to leave a legacy that endures beyond the limits of time? These are the discussions we should be having, the conversations that push us beyond the ordinary and into the realm of the extraordinary. This is an invitation to question, to explore, to debate, to share perspectives on the greatest mysteries of existence. Whether you are a scientist, a philosopher, an artist, or simply someone who has looked up at the stars and felt something indescribable, your voice matters. What do you think lies beyond the edge of the observable universe? Do you believe that we will one day uncover the final ultimate theory of everything, or will the mystery always elude us, forever just beyond our grasp? If we do find answers to the biggest questions, will they bring us comfort, or will they challenge everything we thought we knew? The universe is not just out there, distant and untouchable. It is here, within us, woven into our very being. We are the product of cosmic evolution, conscious stardust capable of reflecting on its own origins. And that, in itself, is a miracle beyond measure. But the story is far from over. There are still galaxies waiting to be discovered, forces yet to be understood, cosmic frontiers yet to be crossed. The future of our understanding is in our hands, shaped by our willingness to question, to learn, to reach beyond the known, and embrace the unknown. So let us continue the journey, not just as passive spectators, but as active seekers of truth. The next great discovery could be just over the horizon, waiting for those bold enough to ask, to wonder, and to dream. The universe is a cathedral of silence and chaos, a boundless expanse where time stretches and collapses under the weight of cosmic forces beyond human comprehension. To drift through the cosmos, even in thought, is to enter a realm of the unimaginable space where light, after traveling for billions of years, finally reaches the instruments of human observation, whispering tales of ancient galaxies, of stars that lived and died before Earth was even formed, of voids so vast they defy all sense of scale. In the endless black ocean of the universe, great islands of light stretch across the abyss, each galaxy a swirling maelstrom of billions, sometimes trillions of stars, orbiting the gravitational well of a supermassive black hole, an invisible beast lurking at their core. There are places in the cosmos so violent that time itself bends and warps beneath the gravitational grasp of singularities, where the very fabric of space collapses into nothingness, creating a one-way door to the unknown. These black holes, the remnants of once mighty stars, pull everything into their event horizons, places where even light cannot escape. Some theorists believe they could be gateways to other regions of the universe, perhaps even to entirely separate realities, while others see them as cosmic tombs, dead ends where matter is shredded beyond recognition. But the universe is not merely a place of destruction, it is also a place of birth. Within the swirling clouds of nebulae, stars emerge from dense knots of gas and dust, igniting with nuclear fire, their radiation carving luminous paths through the darkness. The Orion Nebula, a celestial nursery just 1,300 light-years away, glows with the fiery brilliance of young stars being born, sculpted by the gravity that has governed the universe since its very first moments. Within these stellar cradles, elements forged in previous generations of dying stars are assembled into new worlds, into the very building blocks of life. Yet for all the places filled with energy and light, there are voids so immense, so profoundly empty, that they challenge the very definition of existence. The Bootes void, a yawning chasm nearly 330 million light-years across, is one of the most mysterious regions of the observable universe. Containing only a handful of galaxies scattered across its incomprehensible vastness, it is a cosmic desert, a place where creation seems to have simply stopped. Scientists speculate on its origins, some believing it to be the result of galaxy mergers over billions of years, while others entertain stranger possibilities, perhaps evidence of unknown cosmic phenomena, or even the signatures of forces yet to be understood. And then there is dark matter, the ghostly substance that makes up most of the universe's mass, yet refuses to reveal itself. We know it is there by the way galaxies rotate, by the way gravity bends light around invisible structures, by the way it influences the movement of the cosmic web itself. But no telescope, no instrument, no experiment has ever directly observed it. It is a mystery on the edge of discovery, a shadow lurking in the equations of astrophysics, daring scientists to unlock its secrets. Some theories propose that dark matter consists of exotic particles that rarely interact with normal matter, while others suggest an entirely new framework for gravity, a reimagining of the fundamental forces that shape reality. The pursuit of these answers has been the work of many brilliant minds, pioneers who have gazed into the night and sought to understand the hidden mechanisms of the cosmos. Albert Einstein, whose theories of relativity revealed that space and time are not fixed but fluid, shaped by the presence of mass and energy, provided the foundation for much of modern cosmology. Edwin Hubble, peering through the great lens of the Mount Wilson Observatory, discovered that galaxies are not static but moving away from us, revealing the expansion of the universe and paving the way for the Big Bang Theory. Georges Lemaître, a Belgian priest and physicist, was one of the first to propose that the universe began as a single-pointer cosmic seed that exploded outward, growing into the vastness we see today. Arno Penzias and Robert Wilson, through what seemed to be an ordinary radio signal, stumbled upon the faint whisper of the early universe itself, detecting the cosmic microwave background radiation, the afterglow of the Big Bang, the last echoes of the universe's fiery birth. Now, in the modern age, the search continues. Scientists at the European Organization for Nuclear Research, CERN, smash particles together at nearly the speed of light, hoping to glimpse the fundamental building blocks of reality. The James Webb Space Telescope stretches its golden mirrors into the darkness, capturing images of galaxies as they existed over 13 billion years ago, peeling back the layers of time like an ancient manuscript, each page revealing a new chapter in the story of existence. The tone of cosmology has always been one of awe and relentless curiosity. We are drawn to the stars not just for answers, but for the questions they inspire. Every discovery, every revelation about the nature of the cosmos, forces us to reconsider our place within it. Are we alone in this endless expanse? If life arose on Earth, could it not also emerge on the thousands of newly discovered exoplanets orbiting stars just like our own? Or are we a singular anomaly, an impossibly rare coincidence, the only minds capable of contemplating the vastness in which we exist? And what of the ultimate fate of the universe? Will it expand forever, its galaxies drifting apart until the sky grows dark, until even the last remnants of stars fade away, leaving only a cold, empty void? Or will gravity, the ancient sculptor of all things, one day reverse the expansion, pulling everything back into a final cataclysmic collapse, an end that may also be a beginning? These are questions without final answers, mysteries still waiting to be unraveled. To step into the cosmic landscape is to surrender to the infinite, to feel the weight of eternity pressing down, to recognize that our time is but a flicker in the grand expanse. But it is also to embrace the profound beauty of knowing, of seeing, of understanding. The universe is not silent. It speaks in the language of physics, in the glow of distant stars, in the invisible pull of forces we are only beginning to comprehend. It is a mystery, but it is a mystery we are meant to explore. And with every question asked, with every new star charted, we take another step into the infinite unknown. The search for the true edge of the universe is a journey fraught with paradoxes, contradictions, and limitations that stretch the boundaries of human understanding. We look outward, beyond the reach of our instruments, beyond the visible galaxies scattered across the vastness of space, searching for an ultimate boundary, a final frontier that will reveal the full extent of existence. Yet, the deeper we look, the more elusive this edge becomes, dissolving into questions that challenge the very foundations of physics. The observable universe, a sphere roughly 93 billion light-years across, is not the full extent of reality, but only the region from which light has had time to reach us. Beyond this horizon, space continues, perhaps infinitely, perhaps folding back on itself in ways we cannot yet comprehend. But the true conflict lies in whether we will ever be able to know with certainty what exists beyond, or if the universe itself has placed insurmountable barriers between us and the answers we seek. One of the earliest hints that our search for an ultimate edge may be doomed to failure comes from the discovery that the universe is expanding, not just at a steady pace, but accelerating, driven by a mysterious force known as dark energy. In 1929, Edwin Hubble observed that galaxies are moving away from us, and the farther they are, the faster they seem to recede. This discovery shattered the notion of a static universe and introduced a troubling implication. There are regions of space that are moving away so rapidly that their light will never reach us, forever beyond our ability to observe. The universe, rather than opening up to us, is slipping through our fingers, with entire galaxies vanishing beyond a cosmic event horizon, lost to time. If this acceleration continues indefinitely, the observable universe will shrink in relative terms, meaning that future generations may see a cosmos almost empty, the great structures of today fading into an unreachable void. What then does it mean to search for the edge of something that is constantly stretching, an infinite horizon that recedes as we approach? But the paradox is run deeper than cosmic expansion. At the heart of physics lies a conflict between the two great theories that define our understanding of reality: general relativity and quantum mechanics. General relativity, Einstein's masterpiece, describes the universe on the largest scales, explaining the curvature of space, the bending of light, the motion of galaxies. Quantum mechanics, in contrast, governs the smallest scales, the behavior of subatomic particles, the uncertainty and randomness that defy classical intuition. Both theories have been tested to extreme precision, yet when brought together, they refuse to align, breaking down into infinities and contradictions that suggest an incomplete understanding of reality. Nowhere is this conflict more evident than in the study of black holes regions of space, where gravity is so strong that even light cannot escape. According to general relativity, anything that falls into a black hole is lost to the universe forever, its information erased beyond the event horizon. Yet, quantum mechanics dictates that information cannot be destroyed, leading to a contradiction known as the black hole information paradox. If our most fundamental theories cannot reconcile their differences, what other unknown contradictions might lie ahead? And if we cannot resolve the deepest mysteries of physics, how can we ever hope to define the true nature of the universe's boundaries? Even if we assume that a final theory of everything will one day emerge, we remain bound by the limits of observation itself. The universe has a built-in constraint: the speed of light. Every piece of information we receive, every distant galaxy we observe, is an image from the past, frozen in time. The farther we look, the further back we see, until we reach the cosmic microwave background, the afterglow of the Big Bang, a relic from when the universe was only 380,000 years old. Beyond this point, the universe was opaque, a dense plasma that no photon could traverse. This marks an observational wall, a cosmic curtain that obscures everything that came before. If there was a time before the Big Bang, if our universe emerged from another, if reality itself is part of a greater multiversum, we may never be able to see it. No telescope, no experiment can peer beyond that veil, making the very origins of the cosmos unknowable, a mystery locked away by the fundamental nature of physics itself. But even within the observable universe, the contradictions deepen. Consider the Fermi paradox, the unsettling question of why, despite the vastness of space, we see no evidence of intelligent life beyond Earth. Our galaxy alone contains hundreds of billions of stars, many of which host planets in the habitable zone, where life as we know it could exist. If civilizations arise with any regularity, the universe should be teeming with signals, vast megastructures, or even interstellar empires. And yet, we hear only silence. This silence raises disturbing possibilities. Perhaps the conditions for life are far rarer than we assume, or perhaps civilizations inevitably destroy themselves before they can reach the stars. Or worse still, what if there are others out there, but the universe is structured in such a way that we are forever separated from them, divided by distances too great, by cosmic censorship, by forces beyond our comprehension? The more we search, the more we realize that there may be fundamental limits to what we can know, that some truths will remain forever out of reach, tantalizingly close, yet always just beyond the horizon. In the end, our pursuit of the universe's edge is a confrontation with our own limitations. We are creatures bound by time, confined to a single planet, armed with tools that, while extraordinary, are ultimately constrained by the very laws we seek to uncover. Each breakthrough in cosmology reveals new depths of ignorance, each answer leading to more questions, as though the universe itself is an infinite puzzle, designed to forever remain just beyond complete understanding. And yet, This is not a reason for despair. The pursuit itself, the endless striving toward knowledge, is what defines us as a species. Even if we never find the true edge of the universe, even if paradoxes remain unresolved, even if the final answers elude us, the act of searching transforms us. It is in the asking, in the wondering, in the relentless push against the limits of understanding that we find meaning. The edge of the universe, if it exists, may never be reached, but the journey toward it will always drive us forward. The quest to define the true nature of the universe, its boundaries, its origins, and its fate has led to some of the deepest conflicts in modern science. At the heart of this struggle lies a fundamental tension between different scientific theories, between the observable and the theoretical, between the mathematical beauty of physics and the harsh reality of evidence. Cosmologists stand at the precipice of the unknown, grappling with questions that seem to defy the limits of human understanding. Is the universe infinite, stretching endlessly in all directions, never looping back upon itself? Or is it finite, with an ultimate boundary, a cosmic edge that we may one day define? Every answer leads to new paradoxes, new contradictions, forcing scientists to navigate a landscape where even the laws of physics may not be as immutable as they once seemed. One of the deepest conflicts in cosmology arises from the fundamental incompatibility between the two great pillars of modern physics: general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, describes the universe on the largest scales, explaining how space bends, how time dilates, how gravity shapes the cosmic web. It tells us that massive objects warp space-time, creating the orbits of planets, the spirals of galaxies, the inescapable grasp of black holes. Quantum mechanics, on the other hand, governs the smallest scales, revealing a world of uncertainty, of particles that exist in multiple states at once, of forces mediated by invisible quanta that pop in and out of existence. These two frameworks have been tested with extreme precision in their respective domains, yet when scientists attempt to merge them into a unified theory, the equations break down. Infinities appear where they should not exist. Space and time themselves seem to dissolve into meaningless chaos. And nowhere is this failure more apparent than when trying to define the very fabric of the universe, what lies beyond the observable. What happens at the smallest and largest scales, whether there is an ultimate boundary or an infinite expanse? This clash extends into the very structure of the universe itself. The standard model of cosmology, known as the lambda cold dark matter (WCDM) model, suggests that the universe began as an infinitely dense singularity with the Big Bang, expanding ever since under the influence of dark energy. Yet even within this framework, critical questions remain unresolved. If the universe is infinite, how could it emerge from a singularity, a single point? If it is finite, what lies beyond its edge? The observable universe, the region from which light has had time to reach us, is only a fraction of the total cosmos. But whether this totality is finite or infinite remains one of the greatest unresolved debates in physics. Some theories, such as inflationary cosmology, suggest that our universe is just one bubble in an endless multiverse, where new universes are constantly being born in an infinite cosmic foam. If true, this would mean that our concept of a cosmic edge is meaningless, as reality itself may be unbounded, stretching beyond any definable horizon. Yet even within this vastness, observational evidence continues to challenge theoretical models. The discovery that the universe's expansion is accelerating, attributed to the mysterious force known as dark energy, has thrown cosmology into turmoil. According to Einstein's equations, the presence of dark energy suggests that the universe will continue expanding forever, galaxies moving apart at ever-increasing speeds, until ultimately, all matter is dispersed into a cold, empty void. This scenario, known as the Big Freeze, suggests that the universe has no final edge, no outer boundary, only an ever-growing emptiness, where even the last remnants of energy eventually fade into oblivion. But this conflicts with other possibilities, such as the Big Crunch, where the expansion of the universe eventually reverses, collapsing everything back into a singularity, or the Big Bounce, where the cycle begins again, leading to an eternal sequence of universes being born and destroyed. Further complicating the picture is the nature of space itself. The geometry of the universe, whether it is open, closed, or flat, determines whether it has an ultimate edge. If the universe is closed, like the surface of a sphere, then traveling far enough in one direction could eventually bring you back to your starting point, implying a finite yet unbounded cosmos. If it is open, like an infinite saddle, it extends forever without repetition. Current evidence suggests that the universe is nearly flat, meaning that while it may be infinite, this conclusion is not definitive. Even more unsettling is the possibility that the universe has additional dimensions beyond the three of space and one of time that we perceive. String theory, one of the leading candidates for a theory of quantum gravity, proposes that reality may consist of extra spatial dimensions, curled up at scales too small for us to detect. If true, our entire understanding of cosmic structure would need to be rewritten. Cosmologists also struggle with the very nature of observational constraints. The speed of light places a fundamental limit on what we can see. No information can travel faster than light, meaning that there are regions of space forever beyond our reach. The cosmic microwave background radiation, the afterglow of the Big Bang, represents the farthest observable light, but what lies beyond remains unknown. Some suggest that the universe may be structured in ways we cannot yet perceive, with hidden dimensions, cosmic strings, or even parallel realities interacting with our own. Others argue that what we see is all there is that beyond the observable universe lies simply more of the same, an infinite repetition of galaxies and voids stretching without end. The deeper we delve into the mysteries of the cosmos, the more contradictions we encounter. The discovery of dark matter, a substance that outweighs visible matter by a factor of 5, yet interacts only through gravity, raises the question of what truly makes up the universe. Every galaxy, every cluster, every large-scale structure is held together by this unseen mass, yet all attempts to directly detect dark matter particles have so far failed. If our best theories cannot explain the dominant form of matter in the universe, how can we trust them to define its boundaries? Some physicists suggest that dark matter is not a form of matter at all, but rather a modification of gravity itself, implying that our understanding of fundamental forces is incomplete. If gravity operates differently on cosmic scales, then the very fabric of space-time may be structured in ways we have yet to comprehend. Even time itself presents a conflict. If the universe is infinite, does time stretch infinitely into the past as well, or did time itself have a beginning? The Big Bang theory suggests a definite start, yet quantum models propose that time may be emergent, an illusion arising from deeper laws of physics. The concept of a multiverse raises the question of whether time operates differently in other regions of existence, whether our experience of past, present, and future is merely a localized phenomenon rather than a universal truth. If time had a beginning, what came before? If it extends infinitely, does that mean that every possible event, every possible variation of existence, has already occurred somewhere in the cosmos? These conflicts between relativity and quantum mechanics, between finite and infinite models, between observation and theory, define the cutting edge of cosmology. Scientists push forward, designing ever more precise experiments, deploying ever more powerful telescopes, hoping that with enough data, with enough refinement, the contradictions will resolve themselves. Yet the possibility remains that some answers will always be beyond reach, that the ultimate nature of the universe, its true structure, its final fate, may forever elude us. And if that is the case, what does it mean for the human quest for knowledge? Can we accept a universe that is fundamentally unknowable, a reality with boundaries we will never cross? The struggle to define the edge of the universe is not just a scientific endeavor, it is a philosophical challenge, a test of the limits of reason itself. It forces us to confront the idea that there may be truths beyond our ability to perceive, that the universe may be structured in ways that defy all human logic. But even if we never find the final answers, the search itself is what drives us forward. Science thrives on conflict, on paradox, on contradictions that demand resolution. And so we press on, reaching for the edge, even if it may never truly be found. If the universe has no edge, if it stretches infinitely in all directions, then we are forced to confront one of the most unsettling and transformative ideas in the history of human thought. It would mean that our reality is boundless, that there is no ultimate horizon, no final frontier, no outer boundary beyond which existence ceases. This realization would have profound consequences, not only for physics and cosmology, but for philosophy, for our place in the cosmos, and for the very nature of existence itself. It would mean that the universe is not a finite construct with a defined shape, but an infinite expanse that extends without end, filled with an uncountable number of galaxies, stars, and possibly even repetitions of our own world. Such a universe challenges everything we think we know about origins, about time, about the very nature of reality. One of the most immediate implications of an infinite universe is that the Big Bang, while marking the observable beginning of our cosmos, would not be the true origin of all existence. If space and time extend infinitely, then it is possible that there was no ultimate beginning, only an eternal past, stretching endlessly before us. The laws of physics, which seem to suggest that our universe emerged from a singularity, may only apply to our particular region of space-time, while other regions of an infinite cosmos may follow entirely different rules. This idea leads naturally to the concept of a multiverse, where different regions of space, separated by distances so vast that no signal could ever pass between them, operate under their own fundamental laws. Some universes might resemble our own, governed by similar physical constants, while others might be radically different, with entirely new forces, dimensions, and structures beyond our comprehension. If the universe is infinite, then the consequences for physics are staggering. The standard model of cosmology, built upon the assumption that the universe had a definite beginning and is governed by a set of universal laws, may need to be rethought. One of the most immediate challenges comes from the idea of energy conservation. In a finite universe, energy can be accounted for, as it is confined within a bounded system. But in an infinite cosmos, where space stretches forever, does energy remain constant, or does it simply extend without limit? And if energy and matter are infinitely distributed, does that mean that every possible configuration of matter must occur somewhere? If true, this would lead to a mind-boggling implication. In an infinite universe, not only is there another Earth somewhere, but there are infinite Earths, infinite versions of you, living slightly different lives, making slightly different choices, existing in infinite variations across the cosmic landscape. But even beyond these existential implications, an infinite universe presents a direct challenge to modern physics. One of the biggest unanswered questions in cosmology is the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. If space extends infinitely, does dark energy exist uniformly throughout, or does it vary in ways we have not yet detected? Does its presence indicate a deeper structure to the fabric of reality, one that hints at unknown forces beyond our current understanding? Theoretical physicists are already grappling with the limits of general relativity and quantum mechanics, searching for a new theory that can reconcile the contradictions between these two foundational pillars of science. But an infinite universe would force an even greater paradigm shift. It would require us to develop models capable of describing an unbounded cosmos, one where the very concept of beginning and end may be meaningless. From a philosophical perspective, an infinite universe raises unsettling questions about our significance. If space extends forever, then our planet, our solar system, our entire galaxy, is just one of countless others, lost in the vastness of an endless reality. This idea can be both humbling and terrifying. On one hand, it reinforces the notion that we are not central to the cosmos, that humanity is just one small part of a much grander existence. On the other hand, it challenges the idea of uniqueness itself. Everything that can happen does happen somewhere in an infinite universe. Then what does it mean to be special? Does individuality even hold meaning in a reality where infinite versions of ourselves exist, each making different choices, each living out parallel lives in distant regions of the cosmos? Some philosophers argue that such a realization could lead to existential nihilism, idea that, in the grand scheme of an infinite universe, nothing truly matters. If every event, every action, every thought is mirrored infinitely elsewhere, then what significance do our lives hold? Yet, others take the opposite view. Rather than diminishing our significance, an infinite universe can be seen as an affirmation of the extraordinary nature of consciousness itself. If the cosmos is boundless, then the emergence of intelligent life of beings capable of understanding the universe, of reflecting on existence, of seeking meaning is an even more remarkable phenomenon. In an infinite expanse of galaxies, the fact that we are here, capable of asking these questions, is itself a profound statement about the nature of life. Perhaps the true meaning of existence is not found in rarity, but in the ability to explore, to question, to seek knowledge. An infinite universe does not render us insignificant, it challenges us to rise to the occasion, to embrace the boundlessness of reality, and push the limits of what is possible. But if the universe is truly infinite, then what does this mean for the future of scientific exploration? If there is no edge, no ultimate boundary, then will we ever reach a point where we can claim to understand the full nature of reality? This is perhaps the greatest challenge that an infinite cosmos presents. If knowledge is boundless, then so too is the quest for discovery. In a finite universe, we might hope to one day map out all of existence, to define its shape, its edges, its ultimate fate. But in an infinite universe, the journey never ends. There will always be more to explore, more to learn, more mysteries to uncover. This does not mean that science is futile. Rather, it means that science is an eternal pursuit, a never-ending process of discovery that stretches beyond any single lifetime, any single civilization, any single epoch of history. The realization that the universe may have no edge also forces us to confront the limits of human perception. We are beings, confined to a specific scale of reality. We exist somewhere between the vastness of galaxies and the subatomic world of quantum mechanics, capable of perceiving only a narrow range of existence. What if there are layers of reality beyond what we can detect, beyond what our instruments can measure? What if our understanding of the cosmos is limited, not by the universe itself, but by the structure of our own consciousness? Some scientists propose that new physics will be required to break through these limitations, to develop theories that transcend human biases and sensory constraints. The search for a unified theory of everything, a single framework that describes all of reality, require a redefinition of the very way we think about space, time, and existence. Ultimately, the consequences of an infinite universe are both exhilarating and deeply unsettling. They challenge our deepest assumptions, force us to reconsider our place in the cosmos, and push us toward new frontiers of knowledge that we cannot yet fully grasp. If the universe has no edge, then the search for understanding is endless, but perhaps that is what makes it beautiful. The journey of discovery does not end. It continues, forever unfolding, always revealing new wonders, new mysteries, new possibilities. The universe, in all its vastness, remains an open question, an unfinished story, waiting for us to write the next chapter. And so we press forward, not seeking an end, but embracing the infinite, knowing that every answer leads to new questions, and that in the search itself, we find meaning. The history of cosmology is marked by a series of turning points moments, when our understanding of the universe was reshaped by unexpected discoveries, challenging our deepest assumptions and forcing us to see the cosmos in an entirely new light. From the realization that the universe is not static to the mind-bending implications of dark energy, these breakthroughs have pushed the boundaries of what is possible, unveiling mysteries that continue to drive scientific exploration. Each revelation has not only expanded our knowledge, but also raised new questions, ensuring that our quest to comprehend the universe remains an ongoing journey. In the modern era, the role of dark energy in shaping cosmic expansion, the rapid development of space-based observatories, and the surprising findings from telescopes like the James Webb Space Telescope, JWST, have marked a fundamental shift in how we perceive the structure, origins, and fate of the cosmos. One of the most significant turning points in cosmology occurred in the early 20th century when Edwin Hubble, using the Mount Wilson Observatory, discovered that the universe is expanding. Before this revelation, the prevailing belief was that the universe was eternal and unchanging, a static expanse of stars and galaxies that had existed in the same form since the beginning of time. However, Hubble's observations of distant galaxies revealed that they were moving away from us, with their light redshifted in proportion to their distance. This discovery not only confirmed the predictions of general relativity, but also laid the foundation for the Big Bang Theory, idea that the universe had a definite beginning and has been expanding ever since. This realization transformed cosmology from a philosophical pursuit into a precise, observational science, paving the way for new questions about the structure and evolution of the cosmos. While the discovery of cosmic expansion was revolutionary, it was only in the late 20th century that scientists encountered one of the most perplexing mysteries in modern physics: the existence of dark energy. In 1998, two independent teams of astronomers, led by Saul Perlmutter and the other by Brian Schmidt and Adam Riess, were studying distant supernovae to measure the rate of cosmic expansion. They expected to find that the expansion was slowing due to the gravitational pull of matter. Instead, their data showed that the universe's expansion was accelerating. This unexpected result shattered existing cosmological models, forcing scientists to propose the existence of a previously unknown force driving this acceleration. They called it dark energy, and its implications were profound. Dark energy, now believed to make up roughly 68% of the universe's total energy content, remains one of the greatest enigmas in physics. Unlike dark matter, which interacts through gravity, dark energy appears to have the opposite effect. It pushes galaxies apart, causing space itself to stretch at an ever-increasing rate. The nature of dark energy is still unknown. Some theories suggest it is an inherent property of space, described by Einstein's cosmological constant, while others propose that it arises from quantum fluctuations in the vacuum of space. There are even more radical ideas suggesting that dark energy could be evidence of a fundamental breakdown in our understanding of gravity at cosmic scales. Regardless of its true nature, dark energy has fundamentally altered our predictions about the fate of the universe. If its influence continues to grow, the cosmos could end not in a fiery collapse, but in a big freeze, or even a big rip, where galaxies, stars, planets, and eventually, even atoms themselves are torn apart by an unstoppable expansion. As scientists grappled with the mystery of dark energy, technological advancements revolutionized our ability to observe the universe, providing unprecedented insights into its earliest moments and its large-scale structure. The launch of the Hubble Space Telescope in 1990 marked a new era in astronomy, allowing astronomers to peer deep into the cosmos with unprecedented clarity. Hubble's observations led to some of the most iconic images in modern science, from the breathtaking pillars of creation in the Eagle Nebula to the Hubble Deep Field, which revealed thousands of galaxies in a tiny patch of sky, proving that the universe is far more vast and populated than previously imagined. Yet, even Hubble had its limits, and astronomers long anticipated its successor, the James Webb Space Telescope, JWST. Launched in 2021, JWST was designed to see deeper into the universe's past than ever before, capturing infrared light that has traveled across billions of years. Within months of its operation, JWST had already begun reshaping cosmology. One of its most surprising findings was the detection of galaxies that existed just a few hundred million years after the Big Bang, far more massive and evolved than expected. These discoveries challenge existing models of galaxy formation, suggesting that the early universe may have been much more dynamic than previously thought. JWST has also provided new insights into exoplanets, analyzing the atmospheres of distant worlds with remarkable precision. For the first time, scientists are detecting the chemical compositions of alien atmospheres, searching for biosignatures, possible indicators of life. This technological breakthrough has brought us closer than ever to answering the age-old question of whether life exists beyond Earth. The idea that we may one day detect an exoplanet with a clear signature of biological activity, a world where something is breathing, metabolizing, or transforming its environment, would represent another monumental turning point in our understanding of the cosmos. Beyond JWST, other technological advancements are pushing the boundaries of physics and astronomy. The development of next-generation gravitational wave detectors, such as the Laser Interferometer Space Antenna, LISA, promises to unveil the universe in an entirely new way by detecting ripples in space-time caused by cataclysmic cosmic events. Meanwhile, experiments at the Large Hadron Collider, LHC, continue to probe the fundamental nature of matter, searching for particles that could provide clues about dark matter and other unknown forces shaping the universe. Yet, with each breakthrough comes new challenges. The more we learn, the more we realize how much remains unknown. Dark matter, which comprises roughly 27% of the universe, remains entirely undetected, except for its gravitational influence. The exact nature of dark energy is still an enigma, and quantum physics and relativity remain at odds, each describing reality in ways that seem fundamentally incompatible. The discovery of galaxies that defy our expectations forces us to reconsider the timeline of cosmic evolution. Even our understanding of black hole suns, thought to be relatively simple objects, has been upended by the discovery of their role in shaping galaxies, producing jets of energy that influence cosmic structure on scales beyond previous predictions. Perhaps the most profound realization from these scientific turning points is that our understanding of the universe is still in its infancy. The questions that remain are not merely details to be filled in, but fundamental uncertainties that could lead to entirely new branches of physics. Could dark energy be a sign that our theories of gravity are incomplete? Could the existence of dark matter indicate the presence of hidden dimensions or unknown forces? Could the discovery of extraterrestrial life force us to redefine what it means to be alive, to be intelligent, to be conscious? Each of these possibilities represents a turning point waiting to happen, a future revelation that could once again transform our perception of the cosmos. We stand on the edge of discovery, looking outward into the infinite, knowing that the universe still holds secrets beyond our current grasp. But if history has taught us anything, it is that the greatest discoveries often come when we least expect them, when we dare to ask the impossible, to challenge our assumptions, and to explore beyond the known. The story of the universe is still being written, and with every technological advancement, every new observation, every equation refined and tested, we turn the page to a new chapter. Whether the next great discovery will be the resolution of dark matter, the detection of alien life, or an entirely new force of nature that rewrites physics, one thing is certain: the journey of exploration is far from over. It is in these turning points that humanity finds its greatest strength, not just in uncovering the secrets of the universe, but in embracing the endless mystery that drives us ever forward. The quest to understand the universe has always been shaped by the way we frame the questions we ask. When early civilizations looked up at the night sky, they saw a firmament of fixed stars, believing Earth was the center of creation. When Copernicus proposed a heliocentric model, it shattered that notion and forced humanity to rethink its place in the cosmos. When Einstein formulated general relativity, the idea of space and time as absolute was abandoned in favor of a reality where gravity is the curvature of space-time. Again and again, scientific revolutions have been born not from simply gathering more data, but from shifts in perspective, imagining the fundamental principles that govern our understanding. Could it be that in our search for the edge of the universe, for dark matter and dark energy, for the ultimate nature of reality, we are looking at the problem the wrong way? Are the mysteries of the cosmos not failures of observation, but of interpretation? One of the most radical shifts in perspective comes from the holographic principle, a theory that suggests our universe may be fundamentally different from how we perceive it. The idea emerged from black hole physics, where calculations revealed a paradox. If information is lost inside a black hole, it violates the fundamental principle of quantum mechanics that information must be preserved. Physicists such as Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not their volume. This led to an astonishing hypothesis that all the information contained within a three-dimensional space might actually be encoded on a two-dimensional surface. In other words, the universe, as we experience it, may be a holographic projection of a deeper reality. If true, this could revolutionize our understanding of cosmic structure, suggesting that space itself is emergent, a construct rather than a fundamental property of reality. The implications of the holographic principle stretch far beyond black holes. If the universe operates like a hologram, then its very fabric might be fundamentally different from what we assume. Quantum entanglement, where particles separated by vast distances appear to be instantaneously connected, suggests that space-time itself may be a secondary effect of deeper, non-local connections. This idea is being actively explored in cutting-edge physics, with researchers suggesting that the geometric structure of space-time emerges from entangled quantum information. If this is the case, then asking whether the universe has an edge might be the wrong question. Space may not be an independent entity at all, but a relational construct shaped by the interactions of underlying quantum states. This shift in thinking extends to our struggles with dark matter and dark energy, two of the greatest unresolved mysteries in modern cosmology. Dark matter, which makes up roughly 27% of the universe's mass-energy content, remains invisible to all known forms of detection, revealing itself only through gravitational effects. Similarly, dark energy, which drives the accelerating expansion of the universe, behaves unlike any known force or substance. What if, instead of searching for exotic new particles, we are misinterpreting the very nature of gravity itself? Some physicists propose that general relativity, while extraordinarily successful, may be incomplete on cosmic scales. Modified gravity theories such as MUND, modified Newtonian dynamics, suggest that the effects we attribute to dark matter could instead arise from subtle deviations in gravitational laws at galactic scales. Others propose that dark energy might not be an actual substance, but a sign that space-time itself is not as smooth and continuous as we assume. The search for a unified theory of physics, the elusive quantum gravity, further challenges conventional viewpoints. Currently, the two most successful theories in physics, general relativity and quantum mechanics, operate in fundamentally different ways. General relativity describes space-time as a smooth, curved fabric that determines how matter moves. Quantum mechanics, by contrast, describes reality as a chaotic, probabilistic field of interactions where particles flicker in and out of existence. Attempts to unify these theories have led to speculative frameworks such as string theory, which posits that all particles are vibrations of tiny, fundamental strings in higher dimensional space. If string theory is correct, then our familiar three-dimensional universe might be just a tiny slice of a much larger, multi-dimensional reality. What we perceive as physical matter may be the result of interactions in dimensions beyond our perception, meaning that the search for the edge of the universe could be meaningless in the way we currently define it. Another radical idea emerging from quantum physics is the concept that time itself may not be fundamental. In classical physics, time is treated as a linear progression, a steady march from past to future. But in quantum mechanics, the nature of time is far more elusive. Some interpretations suggest that time might be an emergent property, arising from the relationships between quantum states, rather than being an independent dimension. If time is emergent, then our entire understanding of cosmic history, of the Big Bang, of expansion, of the evolution of galaxies may be only a partial picture of a much deeper reality. Could it be that what we perceive as the beginning of the universe is simply a phase transition within a greater, timeless structure? These alternative theories illustrate how shifting our perspective reshapes scientific discussions. Rather than assuming we must discover missing components, whether particles, forces, or cosmic boundaries, we must also consider whether our entire framework for understanding reality needs revision. Some of the greatest breakthroughs in history occurred when scientists abandoned old assumptions. Before Einstein, the idea that time could slow down or that space could curve seemed absurd. Before quantum mechanics, the notion that particles could exist in superpositions or affect one another instantaneously across vast distances would have been considered impossible. If we are at a similar turning point in modern cosmology, then the next great leap may come not from confirming our current models, but from breaking free of them entirely. But such shifts are not easy. Science, for all its willingness to embrace new ideas, is also built on centuries of theoretical rigor and empirical testing. Many alternative theories remain speculative, lacking the experimental confirmation needed to supplant existing models. The challenge, then, is to develop new ways to test these ideas, to devise experiments that push the limits of current technology. Future space observatories, quantum computing, and deeper studies of cosmic microwave background fluctuations may provide insights that validate or challenge these emerging frameworks. The search for quantum gravity, the continued refinement of dark energy measurements, and the exploration of the quantum foundations of space-time will be crucial in determining which perspective ultimately prevails. At the core of this shift in perspective is the realization that the universe may not conform to human intuition. We evolved to navigate a world of three-dimensional objects, of cause and effect, of time flowing steadily forward. But nature, at its deepest levels, may not operate according to these familiar rules. Reality may be non-local, information-based, multidimensional, or even holographic. The laws we currently use to describe the cosmos may be approximations of deeper principles, yet to be uncovered. And if that is the case, then the edge of the universe, the nature of dark matter, the meaning of time itself, may all be questions we are only beginning to ask in the right way. In the end, the true shift in perspective may not be about choosing one theory over another, but about embracing the unknown. The greatest scientific revolutions have always required a willingness to question, to doubt, to see beyond the limitations of existing models. Perhaps the universe does have an edge, but not in the way we think. Perhaps dark matter and dark energy exist, but not as we imagine them. Perhaps the very fabric of reality is woven from principles we have yet to discover. Whatever the truth may be, one thing remains certain. Science moves forward not by clinging to what is known, but by daring to see beyond it. For centuries, humanity has built its understanding of the cosmos upon the assumption that the universe is a vast, physical expanse governed by predictable laws, unfolding according to the principles of relativity and quantum mechanics. Every scientific discovery has seemed to reinforce this framework, refining the details but never truly challenging the overarching structure of reality. But what if this assumption is wrong? What if, instead of uncovering the fundamental truths of an external, physical universe, we are instead peeling back the layers of something far stranger, something that defies all conventional expectations? As physicists push deeper into the mysteries of dark matter, dark energy, quantum gravity, and the cosmic horizon, an unexpected twist is emerging, one that suggests the nature of reality may be something far more elusive than we ever imagined. One of the first major cracks in the foundation of classical cosmology came with the discovery of quantum entanglement. In the standard view of physics, objects exist as distinct entities in space-time, with interactions limited by the speed of light. But quantum mechanics tells a different story. When two particles become entangled, they remain connected regardless of distance. Changing the state of one instantaneously alters the other, even if they are separated by galaxies. Einstein famously called this spooky action at a distance, believing it to be an incomplete feature of quantum theory. But decades of experiments have confirmed that entanglement is real, forcing physicists to confront an unsettling implication. Space itself may not be as fundamental as we believe. If information can be transmitted instantaneously between entangled particles, then the very structure of reality may be woven from deeper, hidden layers of connection, suggesting that space-time itself is emergent, rather than fundamental. This realization has led to some of the most mind-bending theories in modern physics. One of the most radical is the idea that our universe is not the only one, that, instead, we exist within a vast multiverse, a seemingly infinite collection of parallel realities where the laws of physics may vary, where entire alternate histories may unfold. The multiverse hypothesis arises naturally from multiple areas of physics, including cosmic inflation, string theory, and the many worlds interpretation of quantum mechanics. According to inflationary cosmology, our universe is just one bubble in an endless cosmic foam, with new universes constantly being born beyond our observable horizon. If this is true, then the idea of an edge to the universe, maybe meaningless or visible cosmos, is merely a tiny fragment of a much larger, incomprehensible reality. Yet, the implications of the multiverse go beyond physics. They strike at the very core of our understanding of existence. If an infinite number of universes exist, then every possible variation of history, every alternate version of reality, must also exist somewhere. There could be other versions of Earth, other versions of you, living out slightly different lives in universes separated by distances so vast that they can never be reached. This realization is both exhilarating and terrifying. It suggests that reality is not singular but a tapestry of infinite possibilities, raising profound questions about identity, free will, and meaning. Are we unique, or are we just one of countless copies? If every possible event occurs somewhere, does anything truly matter? And if the laws of physics can vary across different universes, then what does that say about the nature of science itself? The rules we uncover merely local phenomena, with deeper, unknown principles governing the broader multiversal landscape. But perhaps the most unexpected twist in our search for ultimate truth comes from an even stranger possibility: the simulation hypothesis. Proposed by philosopher Nick Bostrom, the simulation argument suggests that if civilizations advance to the point where they can create highly realistic simulations of reality, then it is statistically more likely that we ourselves are inside such a simulation than that we are in the original reality. The reasoning is simple: if simulated universes vastly outnumber the base reality, then the probability that we are in the base reality is nearly zero. This idea, once confined to science fiction, has gained serious attention from physicists and computer scientists alike. Some researchers have even proposed experimental tests, searching for glitches in the fabric of space-time, looking for signs that the universe operates on a computational framework. The implications of the simulation hypothesis are staggering. If true, then everything we perceive, the stars, the galaxies, the laws of physics, may be nothing more than information running on a higher dimensional substrate. Dark matter, dark energy, quantum uncertainty, could these anomalies be artifacts of the underlying code? If the universe is a simulation, then what is running it? Is it an advanced civilization, a future version of ourselves, or is reality itself a construct of some incomprehensible intelligence, one that operates outside our understanding of time and space? The idea forces us to reconsider the very nature of consciousness. If we are part of a simulation, then is our awareness itself simulated? Or are we independent entities, temporarily existing within a computational framework but capable of transcending it? And if we were to discover the truth, if we were to break free of the simulation, what would that mean? Would we find ourselves in a higher reality, or would we simply dissolve, like a character in a video game who realizes they are not real? Even if the universe is not a literal simulation, the underlying concept that reality may not be what it seems continues to shape scientific thought. The growing field of digital physics suggests that space-time itself may be composed of discrete units, like pixels in a simulation, rather than being smooth and continuous. Some physicists propose that the fundamental laws of nature arise from deep mathematical structures, implying that the universe is fundamentally informational in nature. If this is true, then reality is not a vast physical construct but something more akin to a self-organizing computational system, where information, rather than matter, is the fundamental building block of existence. All of these ideas, the multiverse, the simulation hypothesis, the emergence of space-time from quantum information, lead to a deeper realization about our place in the cosmos. For most of human history, we have assumed that we exist within a single, comprehensible universe governed by universal laws. But now, it appears that reality may be far more complex than that. The rules we observe may not be absolute, but emergent. The universe we see may not be the only one, or even the real one. The very structure of reality may be shaped by principles we have not yet even begun to understand. This realization does not diminish our significance, it expands it. If the universe is a simulation, then we are explorers within it, capable of uncovering the hidden logic that governs our existence. If the multiverse is real, then we are inhabitants of a far grander reality than we ever imagined. If space-time emerges from quantum entanglement, then we are living within a universe where everything is fundamentally connected, where consciousness itself may be woven into the fabric of existence. These ideas do not make life meaningless, they make it even more profound. At this turning point in human knowledge, we stand on the edge of the unknown, realizing that the ultimate nature of reality may forever elude us, or it may be something so different from our assumptions that we have not even begun to ask the right questions. The search for meaning, for answers, for truth, has never been more urgent, not because we are close to solving the mysteries of the cosmos, but because the mysteries are deeper than we ever imagined. The greatest twist of all may not be that the universe is infinite, or that we live in a multiverse, or that we are part of a simulation. The greatest twist may be that the truth is something so profound, so alien to our current understanding, that we have only just begun to glimpse its shape. And in that realization, in that endless pursuit of the unknown, lies the true beauty of existence. Despite the remarkable progress made in cosmology and physics over the past century, the greatest scientific challenges may still lie ahead. Each major discovery has brought new mysteries, deeper uncertainties, and even contradictions that hint at the limitations of our current understanding. The nature of dark matter and dark energy remains unknown. The unification of quantum mechanics and general relativity continues to elude physicists. and the true scale and shape of the universe itself remain speculative. The hurdles that future researchers must overcome are not just about gathering more data, but about developing fundamentally new ways of thinking, inventing technology capable of probing realms we have never accessed, and designing ambitious space missions that push the limits of observation. The next era of scientific exploration will require a synthesis of theoretical innovation, engineering breakthroughs, and interdisciplinary collaboration to tackle the most profound questions ever posed. One of the most immediate limitations facing cosmology is the constraint of observational technology. Despite the astonishing capabilities of current telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, JWST, there are fundamental limits to what they can observe. The biggest challenge is the observable universe itself, a natural boundary set by the speed of light and the age of the cosmos. Because light takes time to travel, the farther we look, the further into the past we see. At a certain point, we reach the cosmic microwave background, CMB, the faint glow left over from the Big Bang, which marks the earliest light in the universe. But beyond this, there is a wall of opacity. Before the universe became transparent to radiation, it existed as a hot plasma that no telescope can see through. This means that the true origins of the universe, the moment before the CMB was released, remain hidden from direct observation. To overcome this limitation, future missions will need to rely on alternative methods of probing the early universe. One possibility is the study of gravitational waves ripples in space-time caused by massive cosmic events. Unlike light, gravitational waves can travel unimpeded through any medium, meaning they could provide a window into the universe's earliest moments. The planned Laser Interferometer Space Antenna (LISA) mission, scheduled for the 2030s, aims to detect gravitational waves from sources such as merging black holes, but a more ambitious project could use similar techniques to search for primordial gravitational waves from the Big Bang itself. If detected, these signals could reveal crucial information about cosmic inflation, the rapid expansion that occurred in the first fractions of a second after the universe began. Beyond the early universe, the search for dark matter represents one of the most pressing challenges in modern physics. Despite making up approximately 27% of the universe's total mass energy content, dark matter has never been directly detected. It does not emit, absorb, or reflect light, making it invisible to telescopes. Its existence is inferred only through its gravitational effects on galaxies and cosmic structures. Current searches, such as underground detectors looking for weakly interacting massive particles, WIMPs, or experiments at the Large Hadron Collider, LHC, have so far yielded no conclusive results. This has led some physicists to propose that dark matter may not be a particle at all, but rather a modification of gravity at large scales. Future research will need to push beyond current methods, perhaps requiring entirely new types of detectors capable of interacting with unknown forces or dimensions. Dark energy presents an even greater enigma. Unlike dark matter, which clusters around galaxies and enhances their gravitational pull, dark energy appears to be a repulsive force, accelerating the expansion of the universe. Its nature remains completely mysterious, with theories ranging from a cosmological constant, an inherent energy of empty space, to exotic fields that vary over time. The European Space Agency's Euclid mission, launched in 2023, and NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, are designed to study dark energy by mapping the large-scale structure of the cosmos. However, the true nature of dark energy may require experiments that go beyond mere observation, perhaps using quantum field theory or even laboratory tests of space-time itself to uncover its deeper properties. Another challenge facing cosmology is the unification of quantum mechanics and general relativity. These two foundational theories of physics work exceptionally well in their respective domains. General relativity describes gravity and the large-scale structure of the universe, while quantum mechanics governs the subatomic realm. However, when applied together, they produce contradictions and mathematical infinities, particularly in extreme environments such as black holes and the Big Bang singularity. String theory and loop quantum gravity are among the leading contenders for a unified theory, but neither has been experimentally verified. To resolve this impasse, physicists may need new types of high-energy experiments, possibly requiring particle colliders far beyond the scale of the LHC or space-based observatories designed to detect microscopic quantum fluctuations in space-time itself. One of the most ambitious goals for future research is the direct exploration of exoplanets and the search for extraterrestrial life. In recent years, thousands of planets have been discovered orbiting other stars, some of which reside in the habitable zones where liquid water could exist. The JWST has already begun analyzing the atmospheres of these distant worlds, looking for chemical signatures of life, such as oxygen, methane, and water vapor. But confirming the presence of life will require next-generation space telescopes, capable of directly imaging Earth-like planets and detecting biomarkers with high precision. NASA's proposed Habitable Worlds Observatory, set to launch in the 2040s, is designed for this purpose, but even more advanced missions, such as interstellar probes or massive space interferometers, may be necessary to obtain definitive evidence. If life is found beyond Earth, it will be one of the most profound discoveries in human history, but it will also raise new questions. If life is common in the universe, why have we not detected signals from intelligent civilizations? This is the essence of the Fermi paradox, which suggests that either intelligent life is extremely rare, or there are factors preventing civilizations from contacting one another. Future research may need to explore not only the existence of extraterrestrial life, but also the conditions that allow civilizations to survive long enough to become spacefaring. One of the most far-reaching challenges in cosmology is the nature of the multiverse. Many theories, including cosmic inflation and string theory, suggest that our universe is not the only one, but part of a vast ensemble of universes with different physical laws. If true, this would challenge the very foundation of cosmology. Why does our universe have the properties it does? Are the laws of physics inevitable, or are they randomly assigned from universe to universe? Testing the multiverse hypothesis is extraordinarily difficult, as direct observation of other universes may be impossible. However, some theories predict that if our universe has collided with another in the past, there may be detectable imprints in the cosmic microwave background. Future telescopes, such as the proposed Cosmic Origins Explorer, could look for such evidence, though proving the existence of other universes may remain an unsolved challenge for centuries. Beyond observational and theoretical challenges, future research must also confront practical and technological hurdles. Space exploration remains costly and complex, requiring international collaboration and long-term planning. Missions to explore the outer solar system, such as sending probes to Europa or Titan, require years of development and funding. More ambitious projects, such as building a telescope on the far side of the Moon to avoid Earth's atmospheric interference, present logistical and engineering difficulties. The construction of massive space-based interferometers to detect fine-scale distortions in spacetime could revolutionize physics, but would require unprecedented advancements in materials science, robotics, and artificial intelligence. Despite these challenges, the future of cosmology is bright. Each unanswered question represents an opportunity for discovery, a frontier waiting to be explored. Scientists are already laying the groundwork for new observatories, advanced particle accelerators, and next-generation space missions that will push the boundaries of what we know. The upcoming decades will likely bring answers to some of the most profound mysteries in science, but they will also raise new questions, as every major discovery has done before. The quest for knowledge is never-ending, and as long as humanity continues to look upward, into the vast unknown, there will always be new challenges, new horizons, and new wonders to uncover. The search for the ultimate nature of the universe has reached a defining moment. Cosmology, once a discipline of speculative philosophy and rudimentary observations, has evolved into a precise science capable of measuring the afterglow of the Big Bang, detecting ripples in spacetime, and peering into the atmospheres of planets orbiting distant stars. But with every new discovery, the universe reveals itself to be even more complex and mysterious than we once thought. The latest competing theories in physics and cosmology suggest fundamentally different visions of reality, some claiming an ultimate boundary exists, others arguing that spacetime itself is emergent from deeper quantum structures. At the heart of this struggle is the greatest challenge of modern physics, the unification of quantum mechanics and general relativity. And yet, for all our advancements, The question remains, will we ever truly find the boundary of existence, or is the nature of reality destined to remain forever beyond our grasp? One of the leading theories that attempts to define a cosmic boundary is the standard LSEDM model, which describes a universe that began with a hot, dense state known as the Big Bang and has been expanding ever since. In this model, the universe has no physical edge in the traditional sense, but there is an observable limit, the furthest point from which light has had time to reach us since the beginning of cosmic time. This observable boundary, currently estimated at 93 billion light-years in diameter, defines the region of the universe we can study. However, according to inflationary cosmology, what lies beyond this visible horizon is likely just more of the serene infinite cosmic expanse, filled with galaxies, stars, and possibly even other regions of space-time with slightly different physical conditions. But while inflationary theory suggests an unbounded universe, other theories propose a more definitive edge to reality. One such possibility comes from certain interpretations of string theory, which posit that space-time itself may be a byproduct of underlying quantum structures. In this view, what we perceive as the universe may actually be a three-dimensional projection of information stored on a lower dimensional surface, much like a hologram. The holographic principle, derived from studies of black hole physics, suggests that all the information contained within our universe could be encoded on a cosmic boundary, a kind of distant event horizon beyond which conventional space-time ceases to exist. If true, this would mean that our search for an ultimate boundary is not about finding the edge of space, but rather the limits of information itself. Competing with these theories is the idea that the universe is not infinite, nor is it fundamentally bounded, but that it is instead cyclical, expanding and contracting in endless cycles. The Big Bounce hypothesis, a revision of the traditional Big Bang model, suggests that rather than originating from a singularity, the universe undergoes repeated phases of expansion and contraction, with each Big Bang following a big crunch from a previous cycle. This would mean that our universe is neither infinite nor contained, but rather part of an eternal rhythm of creation and destruction. If confirmed, this model could explain several outstanding issues in cosmology, including why the universe appears so uniform at large scales, and why the fundamental constants of nature remain finely tuned. Perhaps the most radical of all competing theories is the idea that the cosmos is not fundamentally real in the way we traditionally think of it. The simulation hypothesis, proposed by philosopher Nick Bostrom and increasingly taken seriously by some physicists, suggests that our universe may be an artificial constructor high-resolution simulation running on an advanced computational framework. While initially dismissed as science fiction, this idea has gained traction due to discoveries in quantum mechanics that suggest reality may be pixelated at the smallest scales, much like a digital simulation. If true, then the search for the edge of the universe is not about finding a physical boundary, but rather discovering the architecture of the simulation itself, whether through anomalies in cosmic structure, glitches in fundamental physics, or evidence of an underlying computational substrate. With all these theories competing to define the fundamental nature of reality, one of the greatest unresolved questions remains: how do we reconcile quantum mechanics and general relativity? Einstein's theory of relativity describes the universe on large scales, explaining how space-time bends under the influence of mass and energy. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales, operating with probabilities and uncertainty. But when the two are brought together, such as at the singularity of a black hole, or the moment of the Big Bang, or mathematical models break down, space and time become undefined, and equations spiral into meaningless infinities. The search for a theory of quantum gravity, a framework that unites these two fundamental descriptions of reality, is one of the greatest challenges in physics today. Several competing approaches aim to resolve this conflict. String theory suggests that all particles are not point-like, but instead tiny vibrating strings that exist in multiple dimensions. If true, this theory could provide a natural framework for quantum gravity, explaining how space-time itself emerges from the interactions of these fundamental strings. However, despite decades of research, no experimental evidence has yet confirmed the existence of extra dimensions or the predicted particles associated with string theory. An alternative approach, known as loop quantum gravity, attempts to quantize space-time itself, describing it as a network of tiny loops that weave together to create the fabric of reality. Unlike string theory, loop quantum gravity does not require extra dimensions, and it provides a way to describe the structure of space at the smallest scales. If successful, this theory could offer insights into what happens inside black holes and whether space-time has a discrete, fundamental structure. Yet another approach comes from the study of emergent gravity, the idea that space-time and gravity themselves are not fundamental forces, but rather arise from deeper, microscopic interactions, much like temperature emerges from the collective movement of atoms. If true, this would mean that the laws of physics we observe, including relativity and quantum mechanics, are secondary effects of a more fundamental, hidden layer of reality. As physicists continue their search for a unifying theory, the future of cosmology will likely be defined by new discoveries that challenge and reshape our understanding of the universe. The next generation of space telescopes, such as the Nancy Grace Roman Space Telescope and proposed Louvre Observatory, will allow scientists to probe deeper into cosmic history, searching for clues about the nature of dark matter, dark energy, and cosmic inflation. Meanwhile, advances in quantum computing and experimental physics may provide new ways to test the foundations of space-time itself. Perhaps the final confrontation in cosmology is not just about finding the edge of the universe, but about redefining what an edge even means. If space-time is emergent, then the concept of a physical boundary may be meaningless. If the universe is a simulation, then our search must shift from physical limits to computational ones. If the cosmos is infinite, then we must accept that there will always be more to explore, more to discover, and more mysteries beyond our reach. So, will we ever find a true boundary? The answer may depend on what we mean by boundary. If we seek a physical edge, we may never find one. If we seek a theoretical framework that explains all of existence, we may be forced to confront paradoxes that our minds are not yet equipped to resolve. But if history has taught us anything, it is that every great mystery eventually leads to an even deeper understanding. The universe, in all its vastness, remains an unfinished story, and we are still writing its final chapters. The future of cosmology is not an endpoint but a beginning. Whether through experimental breakthroughs, revolutionary new theories, or an entirely new way of thinking, we stand on the precipice of discovery. The final confrontation is not just with the universe, it is with our own limits, our assumptions, and our willingness to embrace the unknown. In that pursuit, we may never find a final answer, but we will always find something greater than we ever imagined. From the earliest days of human existence, curiosity has been the driving force behind our progress. It is the spark that led our ancestors to look up at the night sky and wonder, to navigate vast oceans without knowing what lay beyond the horizon, to push into the uncharted frontiers of knowledge in pursuit of deeper truths. Exploring the cosmos is not just an academic pursuit, it is a testament to our very nature, a reflection of the unquenchable thirst for understanding that has shaped our civilization. But what is the deeper meaning behind this relentless quest? Why do we feel compelled to seek answers about the nature of reality, even when confronted with the possibility that some mysteries may never be fully unraveled? And in the end, what moral lessons can we take from the vast, indifferent universe that surrounds us? To explore the unknown is to engage in an act of faith, not in the religious sense, but in the belief that knowledge is worth pursuing, even when it may never be complete. For centuries, humans have struggled with questions about their place in the universe, questions that once seemed beyond comprehension. What are the stars? How did the universe begin? Are we alone? Each generation has built upon the knowledge of those before, turning myths into hypotheses, hypotheses into theories, and theories into empirical truths. The discoveries we have, matter gravity, relativity, quantum mechanics, cosmic expansion, have not only changed our understanding of the universe, but have also shaped the way we perceive ourselves. And yet, each new breakthrough only serves to reveal how much we still do not know. One of the great paradoxes of human curiosity is that knowledge and mystery must exist in balance. If everything were known, there would be nothing left to explore, nothing to push us forward. But if everything remained a mystery, we would be paralyzed by ignorance, unable to build upon what has come before. The pursuit of knowledge is not about reaching a final destination, it is about the journey itself, the process of learning, questioning, and refining our understanding. Even now, at the height of our scientific advancement, we find ourselves faced with mysteries so profound that they challenge the very foundations of our thinking. Dark matter and dark energy make up the vast majority of the universe, yet we do not know what they are. The nature of time, space, and consciousness remains elusive. The search for extraterrestrial life has yet to yield definitive answers, despite the growing evidence that planets capable of supporting life are common. These unknowns serve as a reminder that the universe is not something we conquer, it is something we participate in. There is a tendency in human thought to see science as a tool for dominion, a way to exert control over nature. But the more we learn about the cosmos, the more we realize how small and fragile we are within it. The Earth, once thought to be the center of all existence, is now understood to be a tiny pale blue dot, orbiting an ordinary star in a vast and possibly infinite expanse. Our galaxy, the Milky Way, is one among trillions, each containing billions of stars, each with the potential for planets, life, and civilizations we have yet to discover. This perspective is humbling. It challenges our egos and forces us to recognize that we are not the masters of the universe, but temporary observers, fleeting participants in a cosmic drama that has been unfolding for billions of years before us and will continue long after we are gone. But humility does not mean insignificance. If anything, the vastness of the universe makes our existence even more remarkable. The fact that, in a cosmos governed by the cold laws of physics, matter has arranged itself in such a way that life can think, feel, and ask questions is extraordinary. We are not just passive observers of the universe, we are the universe becoming aware of itself. This realization carries profound moral weight. If we are the only conscious beings within the vastness of space, then our responsibility is immense. We are the only known keepers of knowledge, the only known storytellers in a universe otherwise indifferent to meaning. This means that every act of curiosity, every pursuit of truth, every effort to expand human understanding is more than just intellectual progress, it is an affirmation of our unique role in the cosmos. At the same time, our exploration of space teaches us lessons about cooperation, resilience, and the power of collective effort. The greatest achievements in astronomy, physics, and space exploration have not been the work of individuals alone, but of humanity working together. The Apollo missions, the deployment of the Hubble and James Webb telescopes, the search for exoplanets, the study of black holes, all of these endeavors required collaboration across nations, generations, and disciplines. Science is one of the few areas where human beings, despite their many differences, can unite under a shared purpose. The laws of physics do not change based on borders or ideologies. The speed of light, the curvature of space-time, the formation of galaxies, these truths exist independently of our interpretations, reminding us that reality is something we must discover together. Yet, as much as cosmic exploration inspires unity, it also presents ethical challenges. The search for extraterrestrial life raises questions about how we should interact with other forms of intelligence, should we find them. Space colonization forces us to consider the impact of extending human presence beyond Earth, how we treat other planets, how we approach the possibility of altering environments that may harbor life. The increasing role of private corporations in space exploration brings up concerns about the commercialization of the final frontier. As we move forward into this new era, we must ask not just what we can do, but what we should do. The history of exploration on Earth is filled with examples of conquest, exploitation, and environmental destruction. If we are to become a spacefaring civilization, we must learn from our past mistakes and ensure that we approach the cosmos with respect, responsibility, and wisdom. Perhaps the greatest moral lesson from cosmic exploration is that it teaches us patience. The universe operates on timescales far beyond human lifespans, billions of years for galaxies to form, millions of years for planetary systems to stabilize, centuries just to travel to the nearest stars with our current technology. Our search for knowledge will not be completed in a single lifetime, nor even in 100 lifetimes. We are part of a continuum, one chapter in a much larger story. Just as we build on the work of those who came before, so too will future generations build on what we learn today. The ultimate answers the nature of existence. The fate of the universe. The question of whether we are alone may not be discovered in our time, but the act of searching, of asking, of reaching out into the unknown, is itself an essential part of what it means to be human. In the end, the universe does not give us meaning, we give meaning to the universe. The stars do not care if we exist. The laws of physics are indifferent to our hopes and dreams. But we, as conscious beings, have the ability to care, to wonder, to seek understanding. That is our gift. That is our burden. That is what makes us unique. The deeper meaning of exploring the unknown is not just about knowledge, it is about growth. It is about pushing the boundaries of what is possible, about embracing the mysteries that challenge us, about recognizing that the pursuit of truth is itself a noble endeavor, even when the answers remain elusive. So, as we continue to gaze into the depths of space, as we send new probes, build new telescopes, and formulate new theories, we must remember that the universe is not just something to be measured, and mapped, it is something to be experienced, something to be revered, something that reminds us of both our smallness and our greatness. The balance between knowledge and mystery is what keeps us searching, what keeps us striving, what keeps us human. And in that search, in that striving, we find not just the story of the cosmos, but the story of ourselves. The pursuit of knowledge is, at its core, a journey without end. Every discovery, every breakthrough, every moment of clarity is followed by a deeper mystery, a new frontier that challenges our understanding. As we stand at the edge of what is known, peering into the abyss of the unknown, we must ask ourselves, should we seek a final answer, a closed conclusion to our cosmic questions, or should we embrace the mystery, allowing it to remain open-ended, an eternal invitation to explore? The value of leaving questions unanswered is not in resigning ourselves to ignorance, but in acknowledging that the universe is far greater, far stranger, and far more complex than any one perspective can fully grasp. Science, at its most profound level, thrives on the unknown. It is not merely a process of accumulating facts, but of challenging assumptions, refining models, and pushing the boundaries of what is possible. If the universe had clear, absolute answers, if all its mechanisms were already understood and catalogued, the very essence of discovery would be lost. The reason we continue to explore is not because we expect to reach a final destination, but because the act of searching itself is what defines our progress. Leaving the greatest questions of the cosmos unanswered is not a failure. It is an invitation to future generations, an acknowledgement that there will always be more to learn, more to question, more to wonder about. One of the most powerful lessons in cosmology is that every time humanity has thought it reached the pinnacle of understanding, a new discovery has shattered that illusion. The geocentric model, once taken as absolute truth, was overturned by the heliocentric model, which was then expanded by the realization that even our Sunday is just one of billions in the Milky Way. The Milky Way itself, once thought to encompass the entirety of existence, was revealed to be just one galaxy among trillions. The universe, once assumed to be static, was found to be expanding. Each time, reality has proven itself to be far greater than what we previously imagined. So, why should we assume that our current understanding is final? Why should we expect that there is a neat, definitive answer waiting to be uncovered, when history has shown us that every answer leads only to deeper questions? The biggest takeaways from our exploration of the universe are not just scientifically, are philosophical, even existential. First, we have learned that we are not the center of existence. The vastness of space dwarfs human concerns, forcing us to confront the reality that our planet, our species, our entire history is but a fleeting moment in an unfathomable expanse of time and space. And yet, this realization does not diminish, it elevates us. The fact that we, tiny beings on a small rock orbiting an ordinary star, have the capacity to comprehend the laws of physics, to peer billions of light years into the past, to ask questions about the nature of time and reality itself, is nothing short of miraculous. Second, we have learned that the universe is governed by principles both simple and profound. From the elegant equations of relativity to the unpredictable chaos of quantum mechanics, the cosmos operates according to laws that can be uncovered, studied, and understood. But at the same time, these laws hint at something deeper: hidden dimensions, emergent spacetime, dark matter, and dark energy that defy explanation. We have discovered order within the cosmos, but also paradoxes that challenge our perceptions of reality. Third, we have come to appreciate the delicate balance between knowledge and mystery. There is a beauty in understanding, in uncovering the secrets of nature, in unraveling the complexities of black holes, exoplanets, and fundamental particles. But there is also a beauty in what remains unknown, in the infinite possibilities that lie beyond our reach. The search for life beyond Earth, the quest for a theory of everything, the nature of consciousness, these are questions that may remain unanswered for centuries, or perhaps forever. And yet, that does not make them any less worth asking. So, should the mystery of the universe remain open-ended? Perhaps it is not a question of should, but of necessity. The universe is not obligated to provide us with convenient answers, nor is it structured in a way that conforms to human intuition. The vastness of space, the strange behavior of quantum particles, the potential for multiple dimensions, all of these suggest that reality is not something that can be fully contained within a single framework of understanding. To seek a final, closed conclusion is to limit the scope of our curiosity. Instead, we should embrace the unknown, recognizing that the greatest discoveries may still lie ahead. The future of cosmology, and of science as a whole, will be defined not by reaching a final answer, but by continuing to ask deeper and more fundamental questions. With each new generation, new theories will emerge, new experiments will be conducted, new technologies will allow us to see farther and think bigger than ever before. The search for extraterrestrial life, the exploration of black holes and quantum gravity, the possibility of parallel universes, all of these represent the next frontier in our quest for knowledge. And yet, no matter how much we discover, there will always be more. There will always be mysteries just beyond the horizon, waiting to be explored. In the end, the greatest truth the universe has taught us is that there is no final, truthfully deeper layers of reality waiting to be uncovered. The cosmos is not a puzzle with a single solution, but a vast, infinite landscape of possibility, where every answer leads to a new question, and every discovery reveals new frontiers to explore. This is the essence of science, of philosophy, of human curiosity itself. And as long as we continue to look to the stars, to ask, to seek, to wonder, the universe will never be closed. It will remain, forever, an open invitation, an unfinished story, waiting to be written.